In switched mode converters, we usually introduce the transformers to realize the galvanic isolation between the input and output port. Then how to analyze such a type of converters with transformers? In this section, we are going to lead you to learn the equivalent model of the transformer and analyze the converters with transformer. So first, let's look at the objectives of introducing the transformer isolation. Why we need to have the transformer isolation? So first is mainly due to the safety requirements. So usually we need to have to follow the industrial standard to guarantee that there is galvanic isolation. Between the applicants and the power grid, so that we can use the applicants more safely. And the second objective is that we can achieve the reduction of transformer size. Conventionally, we use the line frequency transformer to implement the galvanic isolation. But in switched mode converters, we can use high frequency transformer. To achieve the same galvanic isolation target. But the high-frequency transformer will bring us lots of benefits, meaning mainly because with high frequency, the transformer core size can be significantly reduced. And the third objective is that we can use the transformer to minimize the current and voltage stress of components. Of current and the voltage stress. Of circuit components. This can be implemented by the transformer ratio. As we know, the transformer turns ratio can help us to step up or step down the voltage. So by utilizing the transformer turns ratio, we can step up or step down the voltage. And this process also comes with the benefits of the reduced voltage and current stresses. And fourthly, we can also, by introducing the transformer to achieve multiple outputs. So this can be achieved by introducing multiple secondary winding. In many applications, we require multiple outputs, like our power slots, right? Power adapters. We need to have multiple outputs, so we can achieve this target by utilizing multiple secondary winding of the transformer. And next, let's look at the equivalent circuit model for a specific transformer. Simple transformer model. So the equivalent circuit for a multi-winding transformer can be equivalent to such a circuit. So this is the primary winding, whose turn number is N1. So this is the common magnetic core. And this is the one of the secondary windings, the common coupling point. So voltage here is V2T. And here is the primary voltage is V1T. And on the same core, we can wind multiple windings at what we mentioned. Right? This is N2. We can have the N3 coupling point. N3 voltage is V3T. Dot, dot, dot means that we can have furthermore secondary windings. So suppose that this is the ideal transformer. For the practical transformer, we will have a physical inductance which exists here. So we mark this as Lm. Lm is called the magnetizing inductance. So the practical transformer model is equivalent to the ideal transformer with a magnetizing inductor. The magnetizing inductor is in parallel with the primary side winding. And we can denote the currents accordingly. So this is the primary side current, I1T. And this is secondary side current, I2T. Third winding, I3T. And this I1T is divided into two branches. So this branch is IMT, which is the current flowing into the magnetizing inductor. And this branch is the current flowing into the ideal transformer primary winding. We call this as I1T, prime T. So based on this simple transformer model, we can derive the relationship between the port voltage. So for example, the primary side voltage divided by primary turn number should be equals to secondary side winding voltage divided by secondary side turns number, and equals to V3T over N3 dot, dot, dot. And also, according to the energy conservation law, we can also derive the relationship between different currents, right? Basically, the product of current and voltage equals to power. The power should be conservation, right? Conservation should be exist. Based on the power conservation law, we can derive the relationship between among those currents, I1 prime, I2 prime, and I3T and I2T, and so on. So basically, the power equals to product of voltage and current, right? So we can have this relationship 0 equals to N1 I1 prime t minus N2 I2 t minus N3 I3 t minus dot dot, in case we have more windings here. Okay. So next, let's look at this component, which we call it as the magnetizing inductance. Lm. So Lm originates from the flux versus the H curve of the transformer. So we can plot the BH curve of the transformer. So the x-axis is the HT. So HT is proportional to the magnetizing current, which is the current flowing through this Lm. And the y-axis is the magnetic flux, BT. BT is proportional to the integral of voltage across the magnetizing inductance or across the primary winding. So the integral of V1 T dt. If we look at the BH curve for the transformer, we will observe two phenomena. One is the hysteresis. One is saturation. So you will see such a behavior. So here is saturation. When the H is large enough, it saturates. And in between the saturation, we have the hysteresis. So there is a hysteresis window here. So here is saturation. And between the saturation, the slope of the flux density versus H is the inductance behavior. So the slope is proportional to the magnetizing inductance. So indeed, this is like a physical inductor behavior. And based on this BH curve, we can see that if the magnetizing current is too large, the H will be too large. Then the inductor will be pushed to the saturation, right? Saturation will happen. So the HT, also too large, causes core saturation. And also, if the transformer is biased at here, then we'll have very little slope. So it means that the Lm is very small. The slope is almost flat in saturation region. So which makes it behave like an effective short circuit. Therefore, we usually don't want to have the transformer to operate in the saturation region. And since this magnetizing inductance is like a physical inductor, so it also obeys the volt-second balance principle. we will have volt-second balance in Lm. So for this inductor, based on the inductor nature, we have the voltage of inductor equals to inductance times di over dt. And the volt-second balance tells us the net change of magnetizing current over one switching period equals to the integral, right? Integral of the voltage divided by Lm. So at steady state, this quantity will be equal to 0. So which is essentially the volt-second balance principle. And furthermore, we can derive that the 0 equals to 1 over Ts, the integral from 0 to Ts, V1 t dt. So this is the means the average voltage across the primary side winding of transformer over one switching period equals to 0 at steady state. So we have a specific name for this phenomenon. We call it the transformer reset. If the transformer reset is not valid, then we'll have volt-second accumulating in this Lm. So with time going on, the current, right, Im will accumulate to a very large value to push the transformer to be biased at saturation region, which is not the normal operating condition. Okay, so this means that the transformer reset means that the DC component of V1 must be equals to 0. Otherwise, the situation will happen. Okay. So now let's summarize the steps to analyze the transformer model. So when we encounter a circuit with the transformer, how should we deal with the transformer? So the procedure is rather standard, actually. It's just 3 steps. Step 1, replace the transformer by its equivalent circuit model, as I plotted here with the Lm. And step 2, we just analyze the Lm. We treat Lm as a usual inductor. And step 3, we apply the volt-second balance principle to the Lm. Such that we can derive the DC steady state model for the transformer-based converter. Okay, so in this subsection, we have introduced the basic equivalent circuit of the transformer. And we have learned the magnetizing inductance and also the transformer reset behavior at steady state. As long as we replace the transformer by its equivalent circuit model in the switch converter circuit, we can utilize the same principles to analyze the isolated DC-DC converter.